Hello again everyone, welcome back to ptet.chemistry channel. So in this reformatted tutorial video, I'll go through this June, meaning it's a summer 20. This is a 9701. This is a paper 11, so it's a multiple choice component for this Cambridge International A-level paper. So a lot of students might think that MCQ is quite easy paper, but in fact it's the most difficult paper. And if you can score full mark by thinking really well in your MCQ, then I can assure that you are definitely an A student, perhaps even an A-star student already. Okay, so anything with one or two mistakes, I will call it a win for a multiple choice paper, to be honest. Anyway, so a lot of it comes down to language and being very careful and knowing what you want to say. So before I start, so you can click the button on the bottom right if you have benefited from any of my tutorial videos to further continue supporting my work, and it all costs nothing at all. And I do appreciate it if you do share the channel widely with all your friends, chat group, juniors, seniors, teachers, relative, whoever else you think might benefit from the range of videos on my channel. So yes, there have been a change in the format in which I do my paper. Some of you might have known that there was a copyright issues well, a few months ago by now, which is why all my tutorials now is just focusing on how I will address the question, which I did before, but this time without showing the question paper at all. So I'm literally starting from scratch all over again. However, it will be some time, and there will come a time when I have enough resources that I can pull out some topical stuff that I can then go through, that I can then process the video and make it more relevant for future learners. So do stay tuned for that. Anyway, let's focus on the questions itself, more on quality rather than quantity. In this first question, so we have ethene. Ethene can be oxidized to epoxy ethane, blah, 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 blah. So essentially, this is a equilibrium question. So if I just write down the equation, and then we can imagine and we can explain what we're trying to say. So we are told that the enthalpy change is minus 107 kilojoule per mole. By default, the enthalpy change given for reversible reactions, if they show it like this means it's for the forward reaction. So this is for the forward reaction. So we know the forward reaction is exo. The forward reaction is exothermic because it releases heat. So this is exothermic and it releases heat. Some of my A-level concept tutorial videos are pretty useful, especially the one on rate versus equilibrium. I do suggest you take a look at it if you're very weak at this particular topic. Yeah. In terms of the explanation, so you want the greatest yield, so be very careful about reading the question. You want to do with equilibrium yield of this C2H4O, which is the epoxy ethane. So we want to push the equilibrium to the right hand side. That's what we want to do. We are told that there are two conditions. There's pressure and temperature. So in terms of pressure, we are looking at the moles of gases. So pressure affect gases. So pressure affect gases. We really must count the mole of gases on the left and on the right. You have 1 mole of gas and half mole of gas on the left. So you have 1.5 mole of gases. Gases are very important in your answers. Some students might not realize it, but gases exert a lot more pressure than liquid or solid. So this is on the left hand side, LHS, and you have 1 mole of gas on the right hand side. So the more molecules of gas, meaning the more mole of gas, therefore the more molecules of gases, therefore they exert greater pressure when they collide with the walls of the container which they are stored in. So there are greater pressure on the left and then on the right because there are more moles of gases on the left and on the right. So what is happening is we want the equilibrium to shift to the right. The right hand side is the side with lesser gaseous of molecule. So this is the lesser gaseous molecules. So we can be thinking about the change is going to be the opposite to this. You want to go to the side with lesser gaseous molecules. This is lower pressure. Therefore, your change has to be opposed. The change has to oppose it. The change is opposite. So meaning to say, our change is going to be higher pressure. So that is what we're looking at, because Le Chatelier principle says when you introduce a change to the equilibrium will try to do an opposite reaction to it. So it will try to reduce, or it will try to decrease the pressure, and therefore in doing so it will push the equilibrium to the side with lesser gaseous molecules to try and decrease pressure. So higher pressure is what we're looking at. So we're left between A and B. So it's A and B. C and D must be out. So between A and B, that is when you need to decide in terms of temperature. In terms of temperature, we need to focus on the forward reaction is exothermic. So well, forward reaction is exothermic. It's probably faster if I just explain it, but I figured it out that it's probably helpful that you know how to explain it, because in a theory paper you'll probably be using this kind of multiple choice or MCQ tutorials where I actually explain a bit more. You'll be revising along the way as I go through these concepts, as if you are revising for theory paper as well, meaning the structured paper. The forward reaction releases heat is exothermic because it's negative in value, so it has a value lesser than 0 there. So forward reaction is exothermic. We want to get more product, so we want to get more C2H4O. This is the product, so we will release more heat because going to the right hand side is going to release more heat. This is happening because what is the change? So change is the opposite, because again we are dealing with Le Chatelier principle. Release more heat. When you release more heat, temperature will increase because you are releasing more heat to the surrounding. So what happens is we want to decrease temperature. So this is the change. When you decrease temperature on the outside, the system of the equilibrium will try and increase temperature by releasing more heat, and in going forward, it's releasing more heat. So when you release more heat, it is favoring the forward reaction and therefore giving you more of the products, meaning higher yield of the product. So we want lower temperature. So between 100 degrees Celsius and 200 degrees Celsius, we are looking at A as the correct answer and not B. Okay, so not B at all, but A, which is lower temperature and higher pressure. So these are the type of questions which involve Le Chatelier principle. So make sure that you can explain them really well, especially in a theory paper. Question 2 is about oxidation number. So this looks like a complicated looking formula, but doesn't matter. We'll break it down one by one. So there is a charge. There's a charge on it. So this is an ion. So overall oxidation state of an ion is going to be equal to the charge of the ion, which is +1. Since they don't put a number, it's +1. What do we have here? We have NH3, which is an ammonia. Ammonia is a molecule, as you know from year 9 structure and bonding, and you have 4 of them. As you know, oxidation number of a compound, meaning to say a molecule in this case with no charge, is going to be 0. The Cl is bonded to the cobalt, so the Cl there has the oxidation state of -1. So overall, what do we have? We have +1, which is the overall oxidation state. Cobalt is what we want. We have 4 ammonia, and then we have 2 of the chloride, and overall equal to +1, which is the charge on the ion. So +1 cobalt, this is going to give you 0. I get cobalt -2 because there's 2 times -1. So move the -2 to the other side, and you get cobalt equal to +3, which is option C. Question 3 is about hybridization as well as bonding. The first thing you should be thinking about when you think about hybridization is to count the sigma bond. So sigma bond is a head-on kind of bond, and this is going to be equal to number of bond pair or number of bonding pairs of electrons, and then you got to count number of lone pairs. So the number of bond pairs and lone pairs, when you add them up together, so number of bond pair plus number of lone pair is equal to number of electron pairs. So the number of electron pairs altogether will tell you, is it sp, is it sp2, or is it sp3? Here you can tell that there is 1 of the s orbital and 1 of the p orbital. So if I just show it, 1 of the s orbital plus 1 of the p orbital give you 2. So this is 2 times electron pairs altogether. So that's how we work out hybridization. We can work it out backward. If you know this, then you know 2 electron pairs is a result of 1 of the s orbital and 1 of the p orbital mixed together or hybridized together. Here you have 1 plus 2, 1 plus 2 give you 3. So you have 3 times electron pair, and for the last one, sp3 is 1 plus 3 give you 4, meaning to say we have 4 times electron pairs. Alright, Electron pairs is the sum of bond pair and lone pair, and for that you can watch more of my fuller explanation, I guess, in a full A-level concept tutorial video called Hybridization, as well as VSEPR. You can find that in that playlist called A-level concept tutorials. Now, what do we have here? They say we are looking at ethene. Ethene is a molecule that's stated in the syllabus. It's C2H4. If I draw it out, it will look like this. If I draw it out in three-dimensional, it will look like this. So H, 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 and H. I'm flipping it sideways so that you can see that there is a pi bond. This is the sigma bond. This is the pi bond. Together, this is one pi bond. Of course, you can also represent it as a species, or sorry, not as a species, but you can represent the pi electrons as electron density above and below the plane. So you can also represent that as like that. So what you call that is one time pi bond. So together they exist as a pair. So this is one time pi bond. This is also one time pi bond. When they overlap sideways, they give you rich electron density above and below the plane of the molecule. And this is the one that makes it rich enough to attack electrophile. And you can follow that up in the electrophilic addition mechanism. Okay, so going back to what we said earlier, count the number of sigma bond. So the number of bond pair is equal to the number of sigma bond. If you count around each carbon, so you're just looking at around each carbon. So look at that carbon there, which is the same as that carbon, by the way. This is symmetrical. There are 3 bond pair because 1 sigma, 2 sigma, and 3 sigma. So 3 bond pair. And there's 0 lone pair because, as we know it, carbon there, the carbon form 4 covalent bond. There's 1, 2, 3, and 4 covalent bond. The carbon has no more electrons left at all in the valence shell. 3 plus 0 give you 3 electron pairs. When you have 3 electron pairs, we know the carbon uses the 2s. This is carbon 2s, and the carbon 2p, you have 2px, 2py, and 2pz. Doesn't matter. You have 3 electron pairs. As we said earlier, if you have 3 electron pairs, you will have 1 plus 2 because you just have one of the 2s orbital to be involved. So it's s, and then how many p is required to combine with 1 to mix with one of the 2s to give you 3. 1 plus 2 equal to 3, so it has to be carbon sp2 hybridization. You're going to mix 2 out of the 3, and then you're going to mix this one together, and you get sp2. So this is going to be trigonal planar, 120 degree, meaning to say you have a trigonal planar 120 degree about the alkene carbon there, and each of the carbon is carbon sp2, and there is trigonal planar 120 degree like that. Anyway, what is this question about? This question is about what is the hybridization. We already gotten it at sp2, but what is the bonding? Let's say in the overall bonding, I have just counted for around 1 carbon, but don't forget that in the overall bonding, you're looking at the whole molecule. So you're looking at 1, 2, 3, 4, and 5 sigma, because here is double bond where 1 is sigma and 1 is pi. So you have 1, 2, 3, 4, 5. You have 5 sigma. So this thing has 5 sigma and 1 pi. So meaning to say our only correct answer must be option B there. Okay. Question 4 is about is it look like ideal gas? It's probably not ideal gas. Is it ideal gas question? Let me think about this. It does look like ideal gas equation, but the temperature is not room temperature. So the temperature is 200 degrees Celsius. The pressure is 101 kilopascal, but this thing is not room temperature. But at this particular condition, under these particular conditions, there is a new molar volume, because molar volume of 24 dm cube per 1 mole is only valid at room temperature and pressure. So when you say molar volume of gas is 24 dm cube per mole, as stated in the periodic table ever since your IGCSE or O-level chemistry. This only is at room temperature and pressure, whereas now you are not at room temperature and pressure, there's a new value with it. However, I think the essence of this question is basically the same. If we look at if we look at E10, which is C2H6, basically CnH2n plus 2, which is an alkane, and then you react it with oxygen, so you're combusting it completely. Complete combustion will give you carbon dioxide and water molecule. And what do we have? We have the volume at start. If I just work with volume first, without worrying about the molar volume, let's work with volume, 10 cm cube, and I have 45 cm cube of oxygen, and volume at the end. So if I gotta balance the equation above, because otherwise I wouldn't be able to do any proper calculation with it. There are 2 carbon there, so I should get 2 CO2. There's 6 hydrogen there, I should get 3 H2O, and then there are 4 oxygen plus 3 oxygen, so there's 7 oxygen altogether. I should get 7 over 2 oxygen, which is 7 over 2 times 2. Because I have a molecule, I get 7 oxygen atoms altogether on the left hand side. So this question is asking you what is the total volume of gas present. Total volume of gas present at the end of reaction. So you got to read this question very carefully. It's the total volume of gas, which can include something that's unreacted. So let's get started. This is our mole ratio, 1:3.5. So 7 divided by 2 is 3.5 mole. If I have 10 cm cube, so let's think about reacted. How much volume is reacted? If 10 cm cube reacted, then I will have 10 times 3.5, which is 35 cm cube of oxygen is required to react with 10 cm cube of C2H6, simply because when there is a new molar gas volume at this particular condition, it's going to be the same for all the gases anyway, under that particular conditions, under the same condition is stated in the question, which means that the mole ratio of the gases is still equal to the volume ratio of gases, something you have learned from year 9 IGCSE or O-level chemistry. This is to do with the volume reacted. I am simply using volume ratio is equal to mole ratio. This is for gases. This only work because these are gases. All right, that doesn't look so good. That looks better. Anyway, so what do we have now? So there's volume reacted, and how much volume is formed. I'm talking about how much volume is formed. 1 mole of this give you 2 moles of CO2. This is liquid, this is H2O, this is liquid at hang on. This is liquid at room temperature and pressure, but at 200 degrees Celsius. If you look at this question, at 200 degrees Celsius, H2O is a gas. H2O is a gas at 200 degrees Celsius. Very, very, very tricky indeed. So if I have 1 mole, I'll get 2 mole. If I have 10 cm cube that reacted, I will get 20 cm cube of the gas. And don't forget that we said that the H2O is also a gas at 200 degrees Celsius because H2O boils at 100 degrees Celsius. 1 mole gives you 3 mole of gas at 200 degrees Celsius. 10 cm cube reacted to give you 30 cm cube, meaning, well, 10 times 3, which is 30 cm cube being formed. This is gas, CO2 gas. This is H2O gas at 200 degrees Celsius. And what does the question want? The question wants how much volume remains. Volume remaining at the end. Volume remaining at the end. This question is very tricky indeed. You put in 10 cm cube. You reacted 10 cm cube. That's why I labeled. And therefore, 0 cm cube of the CXHY. Because you fully use up the E10. You put in 45 cm cube, you only reacted 35 cm cube based on the balance equation. So you're left with 45 minus 35, which is 10 cm cube left. 10 cm cube, O2. O2 is a gas. This is unreacted. This is your product, 20 cm cube. Well, I can just copy down the whole thing. And yeah, I mean, like, if you can do this, you should be able to do this fairly quickly without doing all of these. It's just about me, outlining the whole process that is involved. If you can unlock this question, then there's nothing that can stop you from doing it very quickly. 10 plus 20 plus 30, that will give you 60 cm cube. I bet a lot of students, they might have left out the H2O by mistake because they didn't realize at 200 degrees Celsius this is a gas. Some students might have not realized that the O2 is in excess by around 10 cm cube, which means you have got to add in the 10 cm cube as well. Okay, so the answer for that will be option D there. Question 5, you have two reactions. So you have H2 gas going to 2 hydrogen gas. This question is basically enthalpy changes. There's probably a bit of definitions to do with here. So if molar amounts are used, we are dealing with mole, how can the two energy changes associated with this reaction be described? How are you describing it? Okay, let's look at reaction 1 first, and we call this reaction 2. If I look at reaction 1, I am forming 2 mole of the gaseous atom, 2 mole of the gaseous atom from its element in its standard state. Okay, so I can describe this as the atomization of hydrogen, but I'm forming 2 moles of the gaseous atom. Okay, so I should be thinking about forming 1 mole of the gaseous atom from its element in its standard states under standard conditions for enthalpy atomization. Since I'm forming 2 mole of the gaseous atom from its element in its standard states under standard condition, this is 2 times atomization. Now I can also be thinking about this. This is also equal to breaking 1 mole of the covalent bond into the gaseous atoms, everything left and right in the gaseous state. So this is equal to energy of the hydrogen-hydrogen covalent bond. There's a relationship that you should be able to relate from your AS, as well as something you would carry forward to your A2 under Born-Haber cycle as well. For reaction 2, I can be thinking about the combustion of CO, because I'm combusting this in excess oxygen to give me a product. This is not equal to combustion of, so this is not the combustion of carbon, because I did not start from carbon. This is also not the formation of CO2, because yes, I'm forming CO2, 1 mole of it, but I did not form it from the elements. This is a compound, this is not element, so be very careful about it. Okay, so about all of these changes, so I have A, B, C, and D. So in A, what do I have? I have enthalpy of atomization, I have enthalpy of combustion. So yes, I have atomization, I have combustion. I'm pretty sure that A is my answer already. Let me just go through the rest and tell you why they are wrong. Atomization, yes, for the first part, I can associate it with atomization, which is an S syllabus. Enthalpy of formation, I just told you this one cannot be formation because you are not forming it from its elements, which means enthalpy of formation is the wrong one, so B is out. How about C? If I go through C, C is talking about bond energy. Okay, now I stand corrected. I don't think A is the answer, because if you look at it, the atomization has to be multiplied by 2, because I had a look at C and C looks like the correct answer. So let's just go through C and then we'll think about what is going on. So bond energy represent this, because I think I know what's wrong now. They say molar amount. So it's for 1 mole. Molar amount means for 1 mole. This is for 2 mole. So I think that's why they cannot accept atomization. I think that's probably why they don't want atomization there, because C is perfectly fine as well. Bond energy for 1 mole. And then obviously the second one is the enthalpy of combustion, which is the enthalpy of combustion of the CO. So again, both of these versus these, I would say this is more accurate representation of what is happening in this reaction 1 compared to atomization, which you have to multiply by 2 there. Okay, so between C and A, I would choose C as the correct answer, and D, I can tell you that D is wrong, because even though bond energy is correct definition for the first equation here, enthalpy of formation is not correct, same as what I said just now. Okay, so D must be out, therefore option C is the only correct answer there. Question 6 is about the Maxwell-Boltzmann distribution diagram. So Maxwell-Boltzmann distribution diagram is to do with energy distribution. So talk about energy distribution, which means you need to know how to label this kind of graph. Very, very, very important. And make sure you can freehand sketch it as well. This is going to be energy. Sometimes it's labeled as a speed, where speed or velocity of the particles can be expressed in terms of how fast, well, basically in terms of energy as well, because it's also an expression with temperature, okay, because temperature is a measure of kinetic energy of a particle. This is the number of particles with energy E. So if I start by drawing, well, in fact, they give us two graphs, so like that. And then obviously when I have higher temperature, when I have, oh sorry, one of them looks a bit higher like this. Okay, so we got to know that we have activation energy there. And if you use a catalyst, the activation energy with catalyst will be lower. So it'll be coming around there with a catalyst. This question is not asking you on the use of catalyst. They're asking you lower temperature, number one. Number two, most probable energy. So they are looking for most probable energy. So they are looking for the x-axis. Lower temperature would mean that your whole graph will shift to the left-hand side, because overall the molecules have lesser energy. Because like I said earlier, temperature is a measure of the kinetic energy of the particles. So going that way, this is going to be lower temperature, which means going the other way is going to be higher temperature. Okay, so I'm looking at most probable energy, and there's going to be option C, which is the correct answer there. So in this next question 7, we have a very straightforward question. So we are given this equation where the stat symbols really matter in this case, because we are talking about Kp. Kp is to do with partial pressure, and we always assume that solids and liquids don't have partial pressure. So since this is solid, we can say there's no partial pressure, but we can't take a value of 0 simply because Kp will be partial pressure of H2, partial pressure of CO, and then if you think about the partial pressure of the reactant, that goes at the bottom. And then remember, each of the stoichiometric number in this, well, basically the balance equation has this number in front of each of these formula being 1, so the power is to the 1 for each of these. The thing is, you might think about the carbon being included in there because it's a reactant at the bottom there. But the partial pressure, if we say no partial pressure for solid, if we make that 0, anything divided by 0 is going to give you an infinite number, which will give you an error on your calculator, which is why we take it as unity. Unity meaning we just give it a value of 1, and therefore they don't appear in the, well, they can appear in the actual partial pressure expression, but it's not going to have an effect on the actual partial pressure. So it looks like the unit given in the options A, B, C, they are all in terms of Pascal. So I can think about the partial pressure here in terms of Pascal as governed or as detected by the options given there. Each of them is to the power of 1 as per the expression based on the stoichiometric ratio in the balance equation. So they're looking at the units. So the Pascal and the Pascal can cancel. So you're left with just Pascal, and there's option B, very straightforward as the answer there. So question 8, we have these changes in oxidation number that we need to balance a chemical equation. This is as stated in your syllabus under redox changes. So I'm just copying down the question right now. We're given a lot of these algebraic terms where we need to think in terms of the unknown, the algebra. And all we need is the ratio of A is to B according to the questions. A is to B basically means A over B is equal to something is to something. Okay, so this is called dichromate. I should probably improve my handwriting a little bit. This is called dichromate 6, a very popular oxidizing agent. You got 2 chromium and 7 oxygen, each of which is -2. Overall is -2. So 2 chromium equal to plus 14 minus 2, so that's plus 12. Each chromium is plus 6 there. The vanadium in 2 plus is vanadium plus 2. In chromium 3 plus is chromium plus 3. In VO3 minus, the overall charge of the ion is -1. So you have vanadium plus 3 times -2 equal to -1. Vanadium is equal to plus 6. 3 times -2 is -6. Move to the other side is plus 6 -1. It's going to be plus 5. As you could see, the chromium plus 6 to chromium plus 3 is a reduction. So this is reduction. But be very careful Because here, this is for each chromium. For each chromium, you have 2 chromium, and don't forget you have this multiple in front as well, so that you need to consider. So it is from plus 6 for each chromium, multiplied by 2 because you have 2 chromium, each of which is plus 6, and then you got the number in front, which is A, which is the unknown. It is going to plus 3, which is for 1 chromium, but you got a D multiple in front, so it's going from that thing on the left to plus 3 times D on the right hand side. Anyway, the other thing that we are looking at is from the vanadium plus 2 going to the, oops, I don't intend it to be that bad. Anyway, from here to here, we have B multiple of the plus 2, and we have E multiple of the plus 5. So this is the oxidation. And it is from plus 2 times B, because you have B multiple in the balance equation. And this is going to E multiple of plus 5, each of which you only have 1 vanadium, unlike the chromium one, which is very, very tricky, but it's simply because this is for 1 chromium atom. You got 2 chromium, and you got A multiple of it. So we're going to do a little bit of algebra, and you can also think in terms of balancing equation. So that was in terms of oxidation number. If you think about in terms of balancing equation, all the chromium comes from the chromium. So if all the chromium comes from the chromium, so count the number of chromium, and I hope you can see that there are 2 times A, there's 2A chromium on the left hand side, and it must be equal to, well, 1 times D, which is 1 chromium on the right hand side. So that is a very important relationship that we have obtained. The next one is on vanadium. So if you count vanadium in the balance equation, you got B multiple on the left is equal to E times 1, which is, well, B is equal to E because your vanadium needs to be balanced out as well. So you got the other relationship there. And we can imagine that we want A and B. So we're going to substitute the 5E to become 5B. Okay, so basically 5E is equal to 5B because B is equal to E in terms of the number of atoms. Whereas 3D is equal to 3 times 2A. So this is equal to plus 3 times 2A because 1D is equal to 2A. So this is equal to plus 6A. Anyway, looking at the changes in oxidation number. So changes in oxidation number must be balanced. Changes in oxidation number must be balanced. Usually we do this in terms of the electrons, in terms of the number of electrons on the left and on the right must balance out, and then we can have like a plus whatever, balance out minus whatever. So there is the changes in oxidation number, balancing out the changes in oxidation number, overall equal to 0 in a redox equation. I have to sum this up together, equal to 0. That means, let's see what's going on. The change is from this to this. So if I do plus 6A, which I obtained from here, okay, I already summarized it in terms of A because all I need is A over, well, A is to B or A over B in the question. So I change everything which is not A or B into something which is A or B. So there is the final minus the initial. So that's minus plus 12A. So this is equal to plus 12A. So there's the change there. And then this is going to be minus 6A. On the other side, I have the black color one, which is going from this to this. So plus 2B to 5B. So there's plus 5B minus plus 2B. This is equal to 3B. I do think that I do have to add them up together. So it's minus 6A plus 3B is equal to 0. So 3B is equal to 6A. And ultimately, what do I need? I need A over B. So I need to make A over B as my ratio. So A over B. I move B down there. I move 6 down there. So I get 3 over 6. And I hope now you can see that that should be very straightforward now. So A over B can be simplified as 1 over 2. Or you can say A is to B is to 1 is to 2. And this is option B as your final answer. Okay, so I guess what is very tricky about is because of the algebra And the trickiest thing of all is there are 2 chromium atoms, of which you have a number of these whole ion. So plus 6 is for one of them, but you have to multiply by 2 because you've got 2 things which have chromium plus 6, each of which is chromium plus 6, so times 2. And you got a multiple of it, that's how you get plus 12a right there. Alright, so that's probably the most confusing bit of this question, using changes in oxidation number to balance chemical equation. Question 9 in the next question. So this looks like ideal gas equation. If I start off with PV equal to nRT, so PV equal to mass over mR times RT. I want the volume of the gas, so I will rearrange the equation to get the volume of the gas. This is in meter cube, but the answer is given in cm cube. The options is in cm cube, but don't forget that in this expression for the ideal gas equation, this unit is in meter cube, as you would have known from the the common units of the ideal gas equation. Before I put in the values, I always like to write out what is going on. So my mass of argon is a monoatomic gas. From your periodic table, you get 39.9, which is gram per mole. Okay, that's the unit. Oops, sorry. Nope. That is the MR actually. I beg your pardon. That is the MR of AR of argon essentially. It's 39.9 gram per mole. What is my mass here? My mass is actually 0.20 gram. My R from the not periodic table, but from the data booklet is 8.31 joule per Kelvin per mole. My pressure is in the right unit already, so it's already in Pascal, where Pascal is equal to Newton per meter square, so that's just the right unit. And to give us the volume in meter cube. Yeah, I mean, I have M, I have R, I have T. Oops, I don't have T yet. Temperature is given in 12 degrees Celsius, so I have to add 273 because the temperature here is referring to Kelvin. So 12 plus 273 give me 285 Kelvin. So all that sum up, you get volume is equal to, if you press all of these correctly, based on M times R times T. So if I just set out the expression now, 0.20 times 8.31 times 285 divided by 100,000 times MR, 39.9. What do I get? I get volume equal to 1.19 times 10 to the power minus 4 meter cube. I have to write down the units so that I'll never ever get confused. The options given are in cm cube. Unfortunately, I never quite remember the conversion factor. I always work it out from scratch. 1 meter is 100 cm. So I'm trying to relate cm cube and meter cube together. So 1 meter is 100 cm. So if I cube both sides, whatever I do on the left, I have to do on the right. 1 cube is 1, meter cube is meter cube. 100 cube, this is 10 square by the way. 10 square is 100, so you get 10 square cube, cm cube, meaning to say 1 meter cube is equal to 10 to the 6 cm cube. Therefore, to convert meter cube to cm cube, what I do is I just multiply by 10 to the 6, and my unit now becomes cm cube. Do this onto your calculator and you will get 119 cm cube, and there's option D as your final answer. Question 10 is about same number of unpaired electrons. Got to write better there. Question 10, so same number of unpaired electrons. With these kind of questions, you really have to write out the electronic configurations. So number of unpaired electrons. If you look at option A, you have aluminium. Aluminium is going to be 1s2, 2s2, 2p6, 3s2, 3p1. So there is one unpaired electron there, because as you know, in the 3p subshell, you have 3 of the p orbitals, and you just have 1 electron in the p orbitals. Being a group 13, it's got 1 electron in the p orbital, being unpaired there. And you got copper, but this is copper 2+. This is a transition metal ion, but of course we start from copper, for example. If I start from copper, I'll have 1s2, 2s2, 2p6, 3s2, 3p6, and then I fill 4s2 and 3d9. And that is exactly wrong, because copper atom copper atom as well as chromium atom has this half shell stability where it's better to pair them up in the d orbital than to pair them up in the s orbital because they repel a lot more. So instead of having 4s2 3d9, you will promote one electrons and pair them up in the d orbitals such that you get 3d10 and 4s1 because you promote one of the s orbital electrons into the 3d. So now this is correct, whereas the previous one with 4s2 and 3d9 is wrong. We fill 4s before 3d, but then we lose from 4s before 3d as well. So essentially what we have then for the copper 2 plus ion, it's going to be all of these the same, which is argon. Then you lose one from the 4s1, and then you lose another one from the 3d9 at 3d10, then you get 3d9. This is going to be copper 2 plus. If we look at the d orbital 3d subshell, you have 5 of the d orbitals. 3d9 is going to have parallel spin, and then 6, 7, 8, 9, you have one unpaired electron there. Yes, this unpaired electron is in the d orbital, this unpaired electron is in the p orbital, but both of them has one unpaired electrons. I'm pretty sure we already gotten to the answer, which is option A. Okay, just very quickly, I can go through the other options and show you that they are impossible to be correct since there's only one correct answer. Calcium is going to be 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. There is no unpaired electrons because they are fully paired up in each of these orbital. Chromium, if I start from chromium, yes, I know the question asks chromium 3 plus. Chromium has got argon, so all the way to the 3p6, and then you fill 4s2, 3d4, and that is wrong again because chromium atom is one of those with the half shell stability, just like copper just now. So instead of 4s2, 3d4, you're going to get 4s1, 3d5. But then you want chromium 3 plus, so you cross one out, cross another one, cross another one. So you're going to get argon 3d3, which means you got 3 unpaired electrons because you got 5 d orbitals in the 3d subshell, 1, 2, 3. So you got 3 unpaired electron, which again does not make sense in terms of what you want, which is same number of unpaired electrons. Part C is again about calcium and nickel 2 plus, so I won't do the same thing with calcium because you have no unpaired electrons for calcium. I can show you for nickel, but always start from the nickel atom, just like the rest of transition metal. So 4s2, 3d, hang on, let me have a look at the periodic table. So 1, 2, 3, 4, 5, 6, 7, 8. Is it? 8. Yep, 8. So nickel 2 plus is going to be, you lose from 4s, and then another one from 4s. There you go, 3d8. 1, 2, 3, 4, 5, 6, 7, 8. You got 2 unpaired electrons, whereas calcium has no unpaired electrons. So that can't be the answer there. I'm running out of space here. Let me see if I can squeeze this a little bit up there. Then I can just fulfill whatever the last bit of the reasoning, which is on Fe3 plus as well as O2 minus. So if I start from Fe, which is argon, 4s2, 3d6, then iron 3 plus is going to be argon, lose one from the 4s, second one from here, third one from there. So 3d5, 3d5 would mean that 5 unpaired electrons. And this is versus O2 minus. This is fully filled outer shell because O2 minus has a noble gas configuration. And when you have noble gas configuration, you got fully filled valence shell. And we got fully filled valence shell, no unpaired electrons. When you got no unpaired electrons versus 5 unpaired electrons, clearly they are not the same. And that was why, option A was the answer already. And if you go through this systematically, once you get A as the answer, you have moved on anyway without checking the rest. It's just about being careful and knowing how to fill in the electronic configurations, including the special electronic configuration of copper atom as well as chromium atom, and you lose from 4s before 3d, just in case you didn't know. All right. So it's got to be option A for this question 10. Question 11. So we have this ammonium chloride. So ammonium chloride giving you the ammonia as well as the HCl gas. They say a total of 2.4 times 10 to the 21. So both of these are gas. That's what they're saying, gas, and they're saying this is solid. So this is gas and gas. They said total 2.4 times 10 to the 21 molecules of gas. Now this question is trying to trick you. They are saying how many hydrogen atoms. So the key thing here really is how many hydrogen atoms in the products. In fact, they say in the gaseous products. Now what are we going to do? I guess we need a mole ratio kind of thing. We want the hydrogen atoms, so be very careful, all right? The mole of hydrogen atoms is to the mole of the gaseous products. So how many moles of gaseous product do we have? In the balance equation, we have 1 and 1. Both of them are gas. So altogether, there are 2 moles of gases. But out of the 2 moles of gases, these are gases, how many hydrogen atoms do I have? 3 hydrogen atoms plus 1 is 4 hydrogen atoms in the 2 gaseous product. So there are 4 hydrogen atoms in the 2 gaseous product. And now I want the number of hydrogen atoms. So the number of hydrogen atoms divided by Avogadro constant is going to give me the mole of the hydrogen atoms. So I'm simply setting up the way I would normally set up my mole ratio label from the balance equation, and then this is in terms of the atoms divided by Avogadro constant, which will give me the actual mole of hydrogen atoms. At the bottom, I have the actual number of gaseous molecules, because these are the total number of molecules of gaseous products, which is the actual number of mole of the gaseous products, only when I divide it by Avogadro constant as well, okay? Anyway, so the Avogadro constant can cancel out. Then the number of hydrogen atoms, if you rearrange your equation very, very carefully, you're going to get 4 over 2 times 2.4 times 10 to the 21, because I can move this up there. Press that into your calculator, and I get this to be 4.8 times 10 to the 21 hydrogen atoms. So be very careful about the keywords there, and that must be option C, which is the only correct answer there. Question 12. So we have a white powder. What do we get? The white powder is a mixture. So it's a mixture of sodium chloride and also sodium iodide. Now when you add AgNO3 to it, so we will get precipitation reaction. So this is the classic test for halide, Cl- and I-. You will get AgCl as well as AgI. Anyway, so after that, what do? You add excess concentrated ammonia, excess as well as concentrated ammonia, and then you get precipitate Y. Only precipitate Y. What is correct about Y? Now what do we know? We know that AgCl dissolve in fact in aqueous ammonia. So when you have concentrated ammonia, AgCl will dissolve. So no more AgCl. Therefore, Y is AgI. If Y is AgI, Y is going to be the yellow precipitate of AgI, and we know that silver chloride dissolve, the white precipitate will dissolve. However, in reality, if you produce a mixture of white and yellow, it's very difficult to actually tell what is white and what is, in fact, it will be clouded by the color of yellow, to be honest, if you have both of these as a mixture. So what do we know? We know that X is the precipitate, so X is going to be these as well as these because they are produced as a mixture. That doesn't look so good. So X is a mixture of 2 ppt, so it cannot be pure. So meaning X is a pure white color, X is a pure silver iodide. A and B is wrong. A and B is wrong. Now when you look at Y has no more AgCl because AgCl is the white precipitate. Within this mixture, they will dissolve in the aqueous NH3, although the white can't be clearly seen due to the contamination with the silver iodide present as a mixture. What is very clear, however, since the sodium chloride dissolve, everything else is just going to be the silver iodide, which is yellow in color. So we're just looking at option D, which is the correct answer for this question 12. Question 13, so we have what looks like a calculation question. So we have ammonium salt. So if I just write ionic equation, which is typically a O level or IGCSE level kind of chemistry, where you react ammonium plus hydroxide. This is the base and this is the acid because that donates the H plus and this accepts the H plus, such that you will form water because OH minus take away the H plus and you form water. When this NH4 plus, which contain dative covalent bond, because dative covalent bond is a AS level concept where you have pick up a H plus with the help of the lone pair on the nitrogen. Now you lose the H plus and you will get back the lone pair on the nitrogen, just like that. And that's how you displace ammonia from ammonium salt with the use of a hydroxide or an alkaline solution. Now, what is this question about? This is a balanced ionic equations and therefore you can use it in your mole calculation. Okay, so very, very important ionic equation here. Which ammonium salt is used? Well, what do we have? We have 6.90 gram of the salt, not the ammonium, but of the whole ammonium salt. And then you get 2.51 dm cube of ammonia at room temperature and pressure. So if I look at that, the mole of ammonia at room temperature and pressure is 2.51 dm cube. I would divide by 24 dm cube per mole because that is the molar volume of gas. Press out the calculator and I get 0.105 mole, give or take. Anyway, so what do I know? I know that my mole of ammonium ion is equal to the mole of NH3, since 1 mole of ammonium ion gives me 1 mole of ammonia. Then I guess what I have then is, actually what do I have? I'm given the MR for each of these, right? I'm given the MR for each of these. So given the MR for each options, what can I do? I guess I can work out the mole of the ammonium carbonate. So that's going to be 6.90 over 96.0. If you press down the calculator, they give me 0.072 mole. I should probably do 3 significant figure based on the appropriate data, 719 mole. And then if I look at B is ammonium chloride, so 6.90 over 53.5. The question is, do I want to be doing this? Anyway, never mind, let me just do for all of them. 6.90 divided by 53.5, I get 0.129 mole. C is 6.90 over 80.0. I get 0.0863 mole. And then last but not least, if I do for D, just for completion, I get 6.90 over 132.1. So these are all mass over MR. And I get 0.0522 mole. What do I notice? I notice that, for all the formula, there is different amount of NH4 plus. For example, this is NH4 plus twice, and then this is CO3 2 minus. I'm trying to show it in terms of the ion, you need 2 of the ammonium, so that's why you have twice the ammonium as the carbonate. The next one is the ammonium chloride, so this is just NH4 plus and Cl minus, so 1:1. This is ammonium nitrate, so again 1:1 because the charge of the cation and the anions are equal. And last but not least, you have twice the ammonium because you have a sulfate, which is SO4 2 minus. So what can I say? Let's see, what can I say? I want to say that, the mole of ammonia is equal to the mole of the ammonium. So this is 0.105. So none of these is 0.105. especially when there's 1-to-1 ratio. When there's one ammonium ion, none of these is 0.105 when they should be equal if these are the answer, which means I can cross out B and C. Now between A and D, the problem really is I have two NH4 plus. So if I look first of all at option A, okay, so left with A versus D. If I look at option A, then remember that my mole of ammonia is only true, this is only true for this B and C, for B and C, but they are not 1-to-1 if you are A and D, because I stand corrected, it's not just for B and C, this is from the ionic equation above, However, looking at the ratio of it, so you can hopefully see that we have multiple of 2, and therefore what actually happened is we want the mole of ammonium. So if you find the mole of ammonium in A is going to be half the mole of the ammonium carbonate, because there are 2 ammonium ions, right? So 0.0719 divided by 2, or you can do the mole of ammonium ions in D is going to be again half this answer. So doing the first one first, I get 0.0360 mole, and doing the second one, I get 0.0261 mole. So what can I say? This is supposed to be the mole of ammonium ion in the molecule, and I want the mole of ammonium to be equal to the mole of ammonia. I want 0.105. So none of these is actually what am I doing? It cannot be half, alright? It has to be twice. I regret this so much. Okay, so I'm making quite a lot of mistakes here. No wonder I couldn't get the answer. There are 2 NH4 plus, that's why we need to multiply by 2. There are 2 NH4 plus, that's why we need to multiply by 2 there to get the actual mole of ammonium ion. I regretted this so much now. Anyway, so as you could see, it's actually quite easy to make mistakes, and sometimes you don't even notice that. Remember earlier, we wanted this thing, we wanted the mole of ammonia to be 0.105. The mole of ammonia comes from the ammonium according to this 1:1 mole ratio in this ionic equation, which you had done in year 9 IGCSE or O-level chemistry. And I've just worked out the mole of each of these ionic solid, each of these ammonium salt solid. But we want the mole of ammonium in the solid. When we got 2 mole of ammonium, we need to multiply 2 times the mole of the solid itself, and the one which gives us the mole of ammonium that corresponded to the mole of ammonia released in this experiment, that is going to be the answer. So that's why we're looking at option D, which is the answer for this question 13. Question 14. Question 14 is about group 2 chemistry. So they say reacts more readily with water. So if you think about the solubility of the group 2 hydroxide, so this is a statement in group 2 chemistry. The group 2 hydroxide become more soluble than group 2. Things like barium hydroxide is going to be pH 14, very alkaline, very basic. That is a result of it being very soluble. Things like magnesium hydroxide, on the other hand, is going to be not very soluble, therefore not very basic. In fact, it's only pH 9. When you dissolve magnesium oxide in water, magnesium oxide can dissolve in water, and then they give you magnesium hydroxide, but there's only pH 9, whereas things like barium hydroxide is formed from barium oxide dissolving in water, and that is very, very strong base because it is becoming more soluble. So we are saying that if I just come up with a trend, and then I can just write it down there, that is becoming more soluble than group 2. Okay, so going back to the table, the oxide reacts more readily with water. This is not very soluble, therefore it doesn't react too readily with water. So between magnesium oxide and barium oxide reacts more readily with water. Okay, and then the lower pH, be very careful. So the Mg or shaken with water, this is going to be P, whereas the barium oxide shaken with water, that's going to be test tube Q. You want the lower pH. Lower pH is going to be this. So this is lower pH, meaning meaning less basic. Okay, lower pH means less basic, as both of these are bases are alkaline, but this is less basic than this, which is a strong base. So we are looking at lower pH, therefore there has to be P, which is this magnesium hydroxide, which is P there. So we're looking at barium oxide and P. This must be option A. So be very careful about reading the question. Yeah. What do we know about question 15? Question 15 is about the chloride. So period 3 chloride. So in a period 3 chloride, what do we know? We know NaCl just dissolve and it doesn't undergo hydrolysis. MgCl2 and AlCl3 as well as SlCl4, PCl5, all of these undergoes hydrolysis, meaning to say the bond will break, and then this thing is not very acidic, it's only pH 6.5. AlCl3 is give you like pH 3, pH 2 sometimes. SiCl, I got this formula wrong, SiCl4 as well as PCl5 or sometimes PCl3 as well. They're going to end up with very, very strong acid. Now the chloride of Z reacts with water to give a solution with a pH less than 5. The key thing there is less than 5. pH less than 5, very strong acid. Whereas this thing is very weak acid. Okay, so do not couple the magnesium in there, so meaning A and C is going to be out. What else can I say? Well, we're looking at B and D now, but then B and D both could be an answer in terms of pH. Okay, I think I missed out one thing. Element Z, the other information is they say the element itself has a giant structure. They don't say which kind. They don't say it's giant metallic or giant molecular. But if you look at the element, so we know MgCl2 is not what we want. We know we have aluminium, silicon, or phosphorus. We also know phosphorus is P4 molecule. And we know that option D is talking about P4. Therefore, you cannot have phosphorus as a giant structure. P4 is a simple molecular structure because it exists as a simple molecule. And having said that, you can cross out D because phosphorus does not have a giant structure. And therefore, we are just looking at aluminium and silicon, which is option B there. So it's just aluminium and silicon left, both of which have a giant structure because this giant metallic structure and this giant covalent structure there. So in the next question 16, we have a couple of these period 3 oxide. So we are looking at the structure of the oxide as well as reacting properties. When we start out with sodium oxide, Na2O, we know that it's a basic oxide because when it reacts or dissolves in water, it doesn't just dissolve, instead it forms NaOH, and we could balance this equation with that, and that is basic, or you will call that alkaline, meaning to say the pH will be, well, actually the pH is around 13 or 14, so there is going to be a strong base. As you know, it dissociates completely into OH minus in solution. Now we know that that giant ionic structure is a structure of that that period 3 oxide because it consists of that lattice of Na plus as well as O2 minus alternating in that giant ionic lattice structure. So it seems like all the properties associated with sodium oxide, all of the columns are correct for A, B, C, and D. Well, let's see what we can say about aluminium oxide. So aluminium oxide is Al2O3 as a result of Al3 plus O2 minus. As you know, you are cancelling out the charges, and that's why I'm bringing down the value and not the charges, because when you're bringing out the value, it simply means you are doing not cross multiply, you are doing this thing called lowest common multiple, which is a primary school mathematics. It means you need 2 Al3 plus and 3 of O2 minus. We know this one is an amphoteric oxide, so it doesn't dissolve in water. It's pH 7 in water because it is insoluble in water as part of your period 3 oxide chemistry. But amphoteric means it can react with acids, it can react with bases, and you should be prepared for the balance equation for when Al2O3 reacts with HCl, for Al2O3 reacting with OH minus. Those are very popular theory level questions, whether you're in paper 2 or paper 4, or in fact any other paper, to be honest, any other theory paper. Now, we also know that as a result of this Al3 plus and O2 minus, it has a giant ionic structure, and as a result of this giant ionic structure, it will have high melting point and also boiling point because you need to break really strong ionic bond, which means we are looking at option C and option A. So that option A must be wrong, and this is option C must be wrong because it will have high melting point. No reaction with water, so that is still correct. Giant ionic, that is still correct, which means we need to look at the last column, which is silicon dioxide. Silicon dioxide, also known as silicon 4 oxide, is actually an acidic oxide. So we know that from O-level as well as IGCSE chemistry, calcium oxide, which you get by decomposing calcium carbonate in the blast furnace when you manufacture iron, it will react with SiO2, which is present as an acidic impurity together with your iron ore, hematite, and they will give you a salt, and that salt will be calcium silicate, and calcium silicate is also known as slag. Well, as part of that molten slag that actually come off, you do not produce water, even though this is neutralization, because this happened at very high temperature in the blast furnace. There's no hydrogen in any of these. There's no water going to be produced by these at all. So this is basic oxide, and you have acidic oxide. What you get is a salt as a result of neutralization. So this is not a new chemistry, it's straight from the chemistry of iron or extraction of iron from O-level or IGCSE level chemistry. So it's not amphoteric, it's acidic oxide, which means we are left with option D, having crossed out the other options from what I discussed earlier. Question 17. We have anhydrous magnesium nitrate. Anhydrous meaning no water of crystallization. So what we have is MgNO3 twice because you have Mg2 plus and NO3 minus. Just like what I did in the previous question, how we come up to the formula is about balancing the charges. So one of the Mg2 plus is balanced out by -1 from one nitrate and another -1 from another nitrate. Okay, so that will give you the group 2 oxide, Mg2 plus O2 minus. That will give you 2 NO2 as well as half O2. If you can't see that, let me try and balance it for you. So this is a solid, is a white solid. This is a brown gas, NO2. And then O2 is obviously a colorless gas because you can't see it. Now you got 2 NO3 minus, so that will give you 2 NO2. After you check all the oxygen, there's 6 oxygen, there's 1 oxygen, there's 4 oxygen. So there's 5 oxygen because of 1 plus 4, it gives you 5 oxygen atom. You need 6 oxygen atoms on the right hand side. So this is 2 oxygen atoms in single molecule. I put a half in order to get half times 2, which will give me 1 oxygen atoms. Adding up to the 5 that I already have, that's how I get 6 oxygen atom on the right hand side total. Now I know this is 0.25 gram, and they ask for the total volume of gas. Total volume of gas. So this is a mole calculation kind of thing. If I just express this as mole of gases over the mole of the magnesium nitrate, so I have not only 2 mole of gas, not only half mole of gas, but I have 2 plus half, which is 2.5 mole of gas that comes from 1 mole of the magnesium nitrate. This is how I always set up my mole equation, my mole ratio. I do everything in one step, but I label what I want. Doesn't matter which way around it is, it follows your label. So these are mole of gases, 2 plus half give me 2.5 or 2.5. This is the nitrate at the bottom, so it's 1 mole at the bottom there. At the bottom, I have the mass, which is 0.25. So I have mass divided by mR, which you can work out the MR from the periodic table. I hope you get 148.3. So obviously you need to work this out yourself given the periodic table, and you can get 148.3 using the A-level periodic table, which is 4 accurate to 1 decimal place. On top, I have the volume of gas, and at room temperature and pressure, I can divide that by 24 dm cube per mole, but all the options are given as cm cube, so I can use 24,000 cm cube per mole, which means this volume is in cm cube because I use 24,000 cm cube per mole as the molar volume. Now we're just rearranging that equation. So volume of gas, I'll bring that up. So it's 2.5 over 1 times 0.25 over 148.3. Then multiply again by 24,000. Press that into your calculator and you will get 101 cm cube. And that is going to be option C there. Question 18. Question 18 is about group 17 chemistry. So you're looking for correct chemistry for group 17. So now, which one can I look at this? It seems like the first one is talking about the solubility of the silver halide. So if I have solubility of the silver halide PPT in ammonia. So we know that silver chloride can dissolve in ammonia. So silver chloride can dissolve in ammonia. Silver bromide doesn't want to dissolve in dilute ammonia. Whereas, it only dissolves in concentrated ammonia. Whereas you have AgI, which is a yellow precipitate, doesn't dissolve at all in concentrated or aqueous ammonia. So the solubility of silver halide decreases down group 17. So it says silver astatite, which is all the way down there. It is not going to be soluble at all, so meaning option A must be wrong, considering that AgI already doesn't dissolve in aqueous ammonia, not even in concentrated ammonia. Okay, in terms of part B and C, I guess we can be thinking about the reactions of these thing as an oxidizing agent. So let's have a look at the ability of the halogen as oxidizing agent. Chlorine is pretty good, and then it gets weaker down group 17. If I have astatine, then or astatine, whatever you call it, it will be there. And concentrated sulfuric acid is an oxidizing agent, but not dilute sulfuric acid. So not the dilute sulfuric acid. And as a result of that, that means option C must be wrong because it talks about the reaction of dilute H2SO4. You will not even get the hydrogen astatite, which you expect to get as the first step in this reaction with the halide ion, because it will act as an acid, but with dilute sulfuric acid that's not strong enough to form you the hydrogen astatite, which is not even acting as oxidizing agent, but it just acting as an acid, this sulfuric acid there. So that's how I can cross out C there because of the word dilute. Now between B and D, I can see that astatine is further down in the group 17, so it's a weaker oxidizing agent than chlorine. So meaning to say astatine cannot oxidize chloride to chlorine. So astatine cannot oxidize chloride to chlorine. Therefore option B must be wrong, which means we are left with option D. And that's because when you have consulfuric acid, it's a stronger oxidizing agent than AT2. So I can give my reason if this is in a theory paper. So consulfuric acid is a stronger oxidizing agent than the halogen itself, therefore can oxidize AT minus to AT2. So obviously this equation is not balanced there. Question 19, we have this question on the idea of increasing melting point. So CCl4, MgCl2, and PCl5. We really must think about the structure and bonding. So CCl4, I hope you would know this chemistry. That is a simple molecule that looks just like methane with 4 bond pair and 0 lone pair, so it's tetrahedral chemistry. And as a matter of fact, because all the 4 atoms are the same, they don't have a difference in electronegativity. Well, there is a difference in electronegativity between carbon and chlorine. You have a polar bond, but you don't have a polar molecule, because the dipoles cancel out since all the atoms are exactly the same in this tetrahedral geometry. Therefore, this is a non-polar molecule. If it is a non-polar molecule, you are just looking at van der Waals forces attraction. Now we also have another molecule here, PCl5. So this one is a trigonal bipyramidal. So it's got a trigonal planar base there, which is 90 degree. But then between, well, in the trigonal planar geometry, in the center, you got another bond angle, which is 120 degree. But similarly, just like what we said about this thing with 0 lone pair, so it's got 5 bond pair and 0 lone pair. Again, the dipoles cancel out. So meaning to say it is non-polar. So dipole cancel out, non-polar, and therefore we are just looking at van der Waals only. For MgCl2, definitely we are looking at a giant ionic structure where you have 2 Cl-. So this is a giant ionic structure. Without any hesitation, you can say this one is going to be the highest melting point because you'll be breaking strong ionic bond, whereas here you're just breaking weak intermolecular forces. For the highest, I'm left with A and D, meaning to say B and C must be incorrect. So B and C are incorrect. Now the job really is to decide. So CCl4 versus PCl5, which one is going to be stronger van der Waals? And van der Waals depend on 2 important factors. Second one is not so important, which is to do with surface area. But what is really dominant is the total number of electron in the molecule. So if I look at these, phosphorus has got 1 extra shell than the carbon. Phosphorus has got more electrons than carbon. In terms of number of electrons, without exactly counting, phosphorus win over carbon. In terms of electrons, 5 times chlorine is more than 4 times chlorine. So overall, in terms of electrons, PCl5 has more total number of electrons than CCl4. Therefore, PCl5 stronger van der Waals. If PCl5 is stronger van der Waals, PCl5 has higher melting point. And between A and D, you're looking at option A because CCl4 has a lower melting point than PCl5, has a lower melting point than MgCl2. So there's going to be option A, and that's the correct answer there. Question 20. So we have organic chemistry here. What are we looking at? Let me just draw it out. So I can obviously, the first thing I do is I need to be able to read skeletal formula. Carbon form 4 bond. Carbon form 4 bond. So here so far it only shows you carbon forming 1 bond. So the hydrogen bonded to carbon are not shown. So there's 3 hydrogen there because carbon form 4 bond. So there's 3 hydrogen there. And then there's no hydrogen there because carbon form 1, 2, 3, and 4. Carbon form 4 bond 1 and 2. So there's 2 hydrogen. Carbon form 4 bond, 2 hydrogen there. Carbon form 4 bond, so 1 hydrogen there. Carbon form 4 bond, 3 hydrogen there. Carbon form 4 bond, 3 hydrogen there. Okay, so altogether I can add up the hydrogen. 3, 4, 5, 6, 7, 8, 9, 10, 11 plus 3 is 14. And there's how many carbon is there? There's 1 oxygen definitely, just that ketone, which I'll come back to it later. And there's 1, 2, 3, 4, 5, 6, 7. There's 7 carbon there. They do want the molecular formula. Molecular formula means the actual number of atoms present in one single molecule. Okay, so that's the definition, the number of atoms in one single molecule. Now I said this is a ketone functional group, and ketone is an important functional group under carbonyl as ketone versus aldehyde kind of chemistry. And this one has no reaction with phalanx, no reaction with toluenes as well. So phalanx is this pale blue solution which contains copper 2 plus, therefore it remains blue. So sometimes they do ask you about observation. You do not get a brick red PPT, but what do you see? You see the phalanx solution has no change, meaning to say it remains blue. So therefore, you are looking at option A. So yes, they don't say about it remaining blue, but it does you no harm to know that the color of this is blue. And if aldehyde is present, then you will get a brick red PPT of a copper 1 oxide, which is Cu2O. Question 21, which statement is correct? So there's a bunch of statements here, but it seems like it's all about naming. So if I look at compound A, it's 2,2-dimethyl propanoic acid. When you're doing this kind of question, it's best if you draw it out, and it's best if you know how to draw skeletal formula. Okay, propanoic acid start from there. Carboxylic acid is CO2H, C double bond O, and then OH. Propanoic 3 carbon, so there's 1 carbon already, so 2 carbon and 3 carbon. And then I got 2,2-dimethyl, so there's 1, 2, and 3. Dimethyl means 2 times CH3 at position 2 and 2, so that is 2,2-dimethyl, because both of these are the same CH3 group, propanoic acid. So they say it's an isomer. It's an isomer of propylmetanoate. Propylmetanoate is an ester. As you know, you name the alcohol first as alkyl, and then you name the carboxylic acid, the second bit, as the carboxylate. If I just draw the ester first of all, I know this is the ester bond that I will break. I got 3 carbon alcohol. So this bit on the right hand side is the alcohol. So 1, 2, 3. I draw a skeletal. 1, 2, 3. CH2, CH2, CH3. Metanoate. There's only 1 carbon. So I already got a mistake there. There should just be 1 carbon for metanoic acid. So now this is what do I know? I have 1, 2, 3, 4. So I have 4 times carbon. And I have 1, 2, 3, 4, 5. I have 5 times carbon. Without even checking the molecular formula, I can tell you that they are not going to be isomer because they don't have the same molecular formula, because they don't have the same number of carbon. Okay, so you should be able to do this fairly quickly if you just draw it. Let me try and move a bit faster now that you are very good at this. So let's start with butane 2-ol. So 4 carbon, OH at position 2. So 4 carbon, there's 1, 2, 3, 4. There's no harm in doing it 1, 2, 3, 4 as well, as long as you know about the position. There's a OH, and there is a methyl 2 times, well, there's 1 times CH3. Methyl is CH3, and it's a position 2. This happens to be a tertiary alcohol because the carbon with the OH is bonded to 1, 2, and 3 other carbon. Now they say hexane 3-ol. So you have 6 carbon, 1, 2, 3, 4, 5, 6. So if I just label it with number, as with any skeletal formula, after you draw it, you should really, put a label on it. Well, I mean, check it to see whether the thing makes sense or not. Now there's only 4 carbon plus 1 carbon. This is 5 carbon total. This is 6 carbon total being hex. So again, it cannot be isomer because the number of carbon is not the same. I should really copy down that whole thing. Let me just copy it down because I want it to be in the same page to make my life easier when I have this as a PDF file later on. I don't want to do that. Okay, just give me a minute. So I mean, this tutorial has gone quite long already, but I mean, my whole idea is for it to help you to break down the concept and be able to do it on your own. So again, 3-methyl butane 2-on. So I have a 4 carbon, and this is a ketone because it ends with on. So 1, 2, 3, 4. So I have a ketone, so C double bond O for the ketone. And I got a 3-methyl, so this is 3-methyl butane 2-on. And it says the isomer of pentanal. Pentanal is a 5 carbon aldehyde. So you would draw aldehyde. 1, 2, 3. Oops, sorry. I don't know why that happened, and I can't get rid of that now. I wonder how I can get rid of that. Okay, I can. All right, okay, I thought I can't get rid of it. 1, 2, 3. Oh no, 4 and 5, and then I have at carbon 1, I have an aldehyde. This is a RCHO. Okay, so there's 5 carbon there, and there is 1, 2, 3, 4, and 5 carbon there as well. So this is a ketone. This is a 5 carbon ketone. This is a 5 carbon aldehyde. I can check the molecular formula. This is C5H. Well, let's check. 3 hydrogen there, carbon from 4 bond. 3, 4, 5, carbon from 4 bond. Carbon from 4 bond, which means 2 hydrogen there, 2 hydrogen there, and 1 hydrogen there. So 3, 4, 5, 6, 7, 8, 9, 10. So C5H10 on. Let's check this. 3 hydrogen there, and then there's 1 hydrogen there because carbon from 4 bond. 3 hydrogen there, 3 hydrogen there. So you got 3, 3, 3 is 9, plus 1 is 10. So C4H10O. They both have the same molecular formula, but different structural formula. In particular, one is a ketone and aldehyde, meaning to say these are functional group isomer that comes under structural isomer, which means D must be wrong. Let me just prove my point that D is wrong. So you got 3,3-dimethyl butane 2 on. I wouldn't be writing out the name, but hopefully you can see it's 1, 2, 3, 4. It's a ketone at position 2, and you got a 3,3-dimethyl. So you have 4 carbon, 5 and 6 carbon. So you got 6 carbon. And then you have pentane 3 on. I think I've miscounted. 1, 2, 3, 4, 5. This is pentane 3 on. And I hope you can see there's 5 times carbon, 6 carbon, 5 carbon cannot be isomer when they don't even have the same number of carbon to begin with. Question 22. This looks like a lot of statement here. They say but 1 in and but 2 in. This reaction is with cold dilute acidified manganate 7. So this is mild oxidation of the carbon-carbon alkene bond. This is but 1 in, 1, 2, 3, 4. When you oxidize it under mild condition, you are going to get diol, meaning to say you become OH and OH across the double bond. This is not electrophilic addition of steam because you're not just having H and OH, you're adding OH and OH above the carbon gain oxygen. This is called oxidation reaction. How about when you have but 2 in, you could have the trans where the CH3 are on opposite side of the carbon-carbon double bond, or you could have the cis. It does not matter because when you oxidize it, then you're gonna lose the double bond anyway, and you will add OH and OH across the double bond, and now you can freely rotate about the single bond now, and therefore it does not matter. Both of them will give you the same product. Okay, so this one is called, the top one is going to be a diol, the bottom one is a diol as well, but this one is butane 2,3 diol, I beg your pardon, butane 2,3 diol, whereas the first one is butane 1,2 diol. So these are position isomers. Okay, they are structural isomers, in particular they are position isomers. The question seems like there is a lot of this thing on primary and secondary and stuff, so let's check it out. This is primary, the one marked in blue is primary alcohol because the carbon with the OH is bonded to one other carbon. This is a secondary carbocation because the carbon with the OH, the green one, the carbon with the OH is bonded to 2 other carbon. So this one is a secondary carbocation, whereas the blue one just now was primary carbocation. Having a look at this thing, the carbon with the OH is bonded to 2 carbon. This carbon with the OH is bonded to 2 other carbon. This is secondary alcohol. This carbon is also bonded to 2 other carbon. That is also secondary alcohol. Nope, I want it to be green. So secondary alcohol and secondary alcohol. So let's see. There's a lot of students, W, X, Y, and Z. So W say 1 diol contains 2 primary alcohol group. W is already wrong because this one contains 2 secondary alcohol group. X say 1 diol contains a primary and a secondary alcohol, So oops, I don't want that airport thing to interfere with me. So Y is going to be correct because of this product here. And they say 1 diol contains 2 secondary alcohol group. So first one should be X and not Y, but Y is also correct with 2 secondary alcohol group. And then they say Z, both alkene exhibit cis and trans. Well, this one has cis and trans obviously, but this one no cis trans because of this thing. Okay, you have a terminal CH2, you have 2 groups, 2 atoms or 2 groups that are the same bonded to one of the carbon-carbon double bond is one of the criteria that you must have different atoms or different groups bonded to the same carbon of the carbon-carbon double bond, meaning to say Z is out, X and Y is going to be option C there. Okay, question 23. So we have 2 bromo, 2 methyl pentane. So the first thing we drew we are going to draw the pentane. 1 2 3 4 5. You have 2 bromo, so put a Br there, and you have 2 methyl, put a CH3 there. Okay, what do we know? When you react with hot concentrated, so this thing is hot and is concentrated and is NaOH, but be careful, it's not in aqueous conditions, it's in ethanol. If it is in ethanol, NaOH in ethanol, it's going to favor elimination. When you have hydrogen, well, when you have halogenoalkane, you're going to eliminate the hydrogen halide, in this case the HBr. We're going to be looking not on this carbon directly, not on the carbon with the halogen, but on the next carbon. So the one marked in pink, the one marked in pink are the same because these are CH3 and CH3. So I could draw a H there, and they will give me the double bond there, which means they will give me this particular product. And there's no cis and trans. You could try and draw the other product here, which will give you the double bond there, meaning to say you have a H there, and it will be the exact same product because what this one is going to be 1 2 3 4 5. There's also 1 2 3 4 5. They are the exact same product. Okay, so the one marked in pink are the same type of carbon. They will give you the same product. Doesn't matter where you get them from. Okay, I'm going to mark the other one now with another color. Let's try black color. I'll also try black color here. I also have another H on this end where I'll get a double bond there. So my other product will be like this because that double bond will be there, and I still have a CH3 and CH3, and this one will be the other product. And I don't have cis and trans as well because this group and this group are the same. Previously, I also don't have cis and trans because that is a CH2 and a CH2, so these are terminal CH2, whereas here these are CH3 and CH3, no cis and trans as well. So there are no cis and trans for any of these products. So there's just one product, and the other one is the other product. So they ask you how many products do you get? Well, you just get 2. We just need to name them. So this is 1 2 3 4 5. The one in black is going to be called 2-methyl, and you have pentene, but you have pent 2-ene because this is 5-carbon alkene with the double bond at position 2 being the lower number. On the other hand, what do we have here? We have 2-methyl, but we have pent 1-ene because your double bond starts with the lowest number there, and it has a methyl group at position 2. So 2-methyl pent 1-ene and 2-methyl pent 2-ene. We are looking just at option B, and you can't really do this question without drawing it. Draw and see it for yourself. Question 24 is about polypropene because they say polypropene is an addition polymer. We should be really thinking about propene. I can't even spell propene properly. So propene is a CH2, CH3, so it's a 3-carbon alkene. All right. So what do we have? We have 3-carbon alkenes going to carbon-carbon, and then reality doesn't matter where I put the CH3 because they are all single bond, they are all rotated like this. This is part of the polymeric chain, so we show it opened without the double bond now. Previously you have trigonoplanar geometry because you got 3 bond pair and 0 lone pair at the carbon sp2, which I'm just going to mark in green there. There's carbon sp2 and carbon sp2. So there's carbon sp2. However, you also have carbon sp3. So that carbon sp3 is tetrahedral 109 degree, but that one is 120 degree, and that is the one that now become 1 2 3 and 4. So now you become carbon with 4 bond pair and 0 lone pair. Now you become tetrahedral 109 degree because your 4 bond pair repel equally. So that is now correct for the polymer chain, which means option A, we already gotten the answer there. Okay, and they say half of them are 109, half of them are 120. That is ridiculous because that CH3 is also part of the original carbon sp3, which is 109 degree there. Okay, and they are all 120 is also wrong because this was originally carbon sp3 with 109 degree and it remained as such. Okay. Question 25. So what do we have here? Alcohol having a formula of C5H12O. You want the yellow precipitate. This yellow precipitate with alkaline aqueous iodine. So this is the iodoform that is being produced. So the iodoform test is for CH3CHOH or CH3CO functional group. This is the methyl ketone test, or the CH3CHOH. This comes under alcohol topic in AS. This comes under carbonyl topic in AS, but they come separately, but you shouldn't be treating them separately. It seems like all the answer here point towards alcohol because all the names in the options, they all have an all. So really we just need to draw and see for yourself. I start from option A. So there is propane 1-ol, so 3 carbon alcohol, and then I have 2,2-dimethyl, so 2,2-dimethyl, 2 and 2-dimethyl, propane 1-ol. I do not have CH3CHOH, A is out. 2-methyl butane 2-ol, so I think I got 1 extra carbon, 1 2 3 4, butane 2-ol, and then 2-methyl. And again, I do not have CH3CHOH because this will imply secondary alcohol. The carbon with the OH is bonded to one and then another other carbon there. Okay. C there is butane 2-ol also, 1 2 3 4. But then the methyl group is at position 3. So I hope you can see that you have a CH3 CHOH. So there's the CH3 CHOH. Remember, carbon form 4 bonds. There's 1 hydrogen there. Okay. So C must be the answer. And D cannot be the answer because pentane 3-ol. So OH there. You have a CH3 CH2 CHOH. You have an extra CH2. You don't have that CH3 CH2 CHOH. So D will not give you the iodoform positive result. Question 26. So we have compound X, and then it seems like X is ester. So all of that refer to ester. I'll just quickly draw what an ester is. So ester is this functional group that when you hydrolyze it, and that's what we're going to do. We're going to do base hydrolysis because we do it in aqueous sodium hydroxide, and that is why we do not get the carboxylic acid. Instead, we get a salt. The salt is because we are doing it in basic condition. Any carboxylic acid that is being formed will be deprotonated by the base to give you salt and also water because they do get neutralized. Okay, and you will get ROH. So this is the alcohol product. Now looking at the question, what are we told? We are told that we get sodium ethanoate. Ethanoate means 2 carbon, 1 carbon and 2 carbon. So there's 2 carbon carboxylic acid, and we have hexane 1-ol. So hexane 1-ol, if I just quickly draw the skeletal formula, HO 1 2 3 4 5 6, 1 2 3 4 5 6. If I quickly draw that skeletal formula, so that's going to look like that and that, so 1 and 2. We know that we have to stitch them up together. So this one is going to lose the H, this is going to lose the OH like that. Well, of course it doesn't have the OH now because it's the salt product. So you gotta combine them together again. I have my carboxylic acid like that. So that's my ester with 2 carbon from the carboxylic acid compartment, and then 6 carbon, 1 2 3 4 5 6, 1 2 3 4 5 6. And then there is my 2 carbon for the ethanoate product. Looking at the options, if you go through the options and count the carbon correctly, and I will get option C. This is option C. Okay. Question 27. So they are looking for something called major product. There's 2 double bond. There's 2 times carbon double bond. You got to be thinking about this thing called Markovnikov addition, Markovnikov rule. Doesn't mean anything unless you can explain the inductive effect of alkyl electron donating group. This is stated in the syllabus. It's one of the most popular question in recent years. You are stabilizing the carbocation intermediate. Okay, so in terms of stabilizing the carbocation intermediate, tertiary carbocation is more stable than secondary, more stable than primary, because there is more alkyl electron donating groups. So in order to do this particular question, let's start by drawing the starting material, which they're given you as skeletal formula. So this is a cyclic ring. It's 6-membered carbon and 7 and 8. So what we could see was important there is the double bond, and the double bond, you could imagine that as you are adding HBr, so the polarity of the molecule is delta plus on the hydrogen and delta minus on the Br. I am just going to draw the one. I'm just going to draw all the products. Think about one of the carbon-carbon double bond first. So if I just focus on this carbon-carbon double bond first, I could add the H there, meaning to say, you add the H there, then you're going to get a plus there. Okay, and then the other one is, I could add the H there, and I could get a plus there. So there are 4 possible combinations, and you can draw all the 4 possible combinations. So meaning to say, let's say I change the position of these, but I keep this one the same. So I still add the H on this carbon there. So I have the plus there. So immediately you can see that this side and this side is the same, but that plus has already swapped around between the 2 different carbon of the carbon-carbon double bond. Let me try and draw another one where if I say this to this one is the same. Sorry, this one is different, but this one is the same. What am I doing here? Let me see. Let me draw that being that, and then I'll swap the H being on that position, and the plus is now on this carbon there. Meaning to say I can copy paste that, and can I? Let me see. And I just swap the hydrogen and the plus there. So it looks pretty much like the same from up there. Going from here to here, the top bit doesn't change, but the bottom bit swap around the plus and where the hydrogen adds. Okay, so these are the 4 different possibilities, and we are looking back at what we said earlier. Tertiary carbocation more stable than secondary, more stable than primary. I'm just going to use a pink color highlighter to find primary carbocation. Okay, let me try actually purple color. Primary for purple. Let's see. So the carbon with the positive charge is bonded to 2 carbons. So there is secondary. The carbon with the positive charge is bonded to 1 carbon. So there's primary there. I have another primary there. And that's everything on primary carbocations. Let me try and put a blue highlighter for the secondary. So the carbon with the positive charge is bonded to 2 other carbon. So that is secondary carbocation, because this carbon with the positive charge is bonded to 1 and 2 other carbon. This is a tertiary carbocation. This is a tertiary carbocation. This is tertiary carbocation because the carbon with the positive charge is bonded to 1, 2, and 3 other carbon. And I have one more secondary carbocation. Last but not least, as I said, is the tertiary carbocation. So, what is it? I don't think that black color is the best color of all. Maybe red color. This is tertiary carbocation. Tertiary, and tertiary. The more tertiary carbocation, the better. So this is tertiary and tertiary carbocation. So meaning your major product is going to be where the Br end up there and where the Br ends up there. So this is going to be your major product, which come from the more stable carbocation. So looking at the options, out of all the options, that looks like option B there. So that's the answer. Question 28. So this looks like a big molecule. Unfortunately, there's no way to do this without drawing the structure. But because I know how to draw skeletals, so it shouldn't take me that long, hopefully. Let me try and get this right. So there's a 5-member ring, and then this is a 4-member ester. Where am I now? I'm there. There's another ester there. Okay, so I think I've got everything. So let's try and think about what functional group is present. So this is an ester, C double bond OO. This is C double bond OO is also an ester. We are looking for chiral center. So I'm just going to look for carbon bonded to 4 different other carbon. Cannot be chiral there because these two are the same. These are CH2, 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 cannot be chiral. This is CH3, cannot be chiral. There's our first chiral center there because this side and this side is different, and it's got a CH3 and it's got this other carbonate, so there's chiral. And then you can imagine that there's another chiral center because that half is not the same as this half, and there's a hydrogen because carbon from 4 bond. And this is also chiral, this is also chiral, whereas chiral. So these are what you call the ring junction. The ring junction is most usually chiral unless you're totally symmetrical. Okay, there's no chiral center there, nothing there, not there because this is a CH2, this is a CH2. So altogether we have 1, 2, 3, 4, 5, 6, and 7. So we're looking at option D, which is 7 chiral center. Usually we'll mark it with asterisk, but since I have highlighter here, it's a lot easier to just do the highlighting. Question 29 is about infrared spectroscopy. With infrared spectroscopy, we are looking for 2 things. The first one is around 3000 to 3500 wave number, and there is something which is strong and broad. Unfortunately, I've just passed over the limit a little bit, but it's still around 3000. It's still around 3000 wave number. There's the unit given in the x-axis, and it's something that you have to accommodate and include in your value because it's part of the description for infrared. All right, so what happened there? That indicates the OH bond. This is OH bond. We still don't know about functional group, and because there's OH bond, we can cross out C, which is an ester, where there's no OH bond. We can cross out D, which is ketone. So propanol is a ketone, is a 3-carbon ketone. There's no OH bond at all. Ethyl ethanoate is 2-carbon alcohol and 2-carbon acid to give you ethyl ethanoate. So ester and propanol there, C and D are out. And now I have to look at another region, and that other region is around 1700 in the spectrum given. So that is strong and that is sharp. That is the C double bond or bond. And looking at option A and option B, option A you have ethanoic acid, option B you have ethanol. This one has no C double bond or, so I can cross out B because the spectrum show very clearly there's C or bond there. So I have C double bond or, I have OH bond, therefore A must be what I'm looking for. Question 30. Question 30 is about reaction scheme. You want an organic anion, so be very careful what the question wants you to do. They don't want a compound, they want an anion, and they want a good yield. So this question is a bit tricky. They want a good yield and they want an organic anion. So typically we're looking at anion because you have acid and then you deprotonate it under basic conditions, then you get a salt. But let's just have a look through the option. You have ethane nitrile. So ethane nitrile is a 2-carbon. It's a 2-carbon C triple bond N. So meaning it's CH3CN. If I draw skeletal, it will look like that, 1 and 2. So 2-carbon nitrile is ethane nitrile. You react it with aqueous NaOH. What you're going to get is you're going to get hydrolysis. It's called hydrolysis of ethane nitrile. So what we get is going to be CH3COOH. However, this is under basic condition, which means we will never get the carboxylic acid, because as soon as you produce that in the presence of the base, you will produce a salt. So there you go. I mean, we get our carboxylate. We also produce ammonia gas as a result of the hydrolysis, where you totally break this C triple bond N and we lose the nitrogen as ammonia gas there. Okay, so this will produce us that salt. So I'm pretty sure we already gotten the answer, but let's go through the other options and think about it. We also have ethane nitrile, but here you have sulfuric acid in option B. This is acid hydrolysis, whereas the first one was base hydrolysis. In acid hydrolysis, you will get, well, the acid itself, the carboxylic acid, and the NH3 might be formed as NH4 twice SO4 because the acid is acidic, NH3 is alkaline, so it will form a salt with the acid in state. Alright, so B cannot be the answer. C, you have ethane with sodium metal. Ethane is CH3CH3, no reaction with sodium because that one is, it looks for OH group and you don't have any OH in alkane chemistry. In part D, so what you have is you have ethanol and you have dilute NaOH. So, you know, even if you try to do elimination, it wouldn't quite work because you have dilute NaOH. They don't mention in ethanol, which most likely implies it's in aqueous. You're already an alcohol, so you don't get hydrolyzed further with OH minus. I would say no reaction there. So very clearly, we're just looking at option A as the only possible answer that will produce us this anion under base hydrolysis of a nitrile. Section B is these last 10 questions where we are comparing statements. So we always compare statement 2 first. So let's get started. We have formation of a positive ion. As usual, when you do this kind of MCQ question, if you don't circle, if you don't underline words or terms, then you might make a mistake here and there. If we look at statement 2, they talk about heterolytic fission. Heterolytic fission is in your introductory organic chemistry. So when we have a covalent bond like this, if you know they have different electronegativity, this is the more electronegative atom, this is the less electronegative atom. When you break that covalent bond, the X will become the plus, the Y will become the minus, while retaining or while obtaining that lone pair that come from that covalent bond. So you do produce a positive ion there. So 2 is correct. If I go to number 1, this is first ionization energy. If I write using Z, the gas atom will go to form Z plus gas plus electron because first ionization energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atom to form 1 mole of gaseous ion with a single positive 1 charge. Option 3 is to do with delta H atomization, which is in the AS syllabus. So example, Cl2 going to Cl gaseous atom, and I'm forming 1 mole of the gaseous atom from its elements in its standard states under standard condition. So I'm forming 1 mole of gaseous atom. So this one is no ion at all, no positive ion. So only 1 and 2 is correct. So I'm looking at option B there. Question 32 is about molecular polarity. So no overall dipole. No overall dipole would mean dipoles cancel out. And when dipoles cancel out, you will get non-polar molecule. Alright, so if I check number 2 first, we have CH4. I'm just drawing the 3-dimensional shape. So we have 4 bond pair and 0 lone pair. So the 4 bond pair will repel equally. And you get a tetrahedral geometry with 109 degree. And we know that yes, hydrocarbons are usually non-polar because oil do not mix with water. And oils are petroleum products, which mostly are alkanes. And alkenes non-polar, no overall dipole moment. But also because, you know, the dipole cancel out each other in this kind of geometry with 0 lone pair, especially when the atoms are all the same in this geometry where there's 0 lone pair there. So 2 is correct. If I check number 1, is boron trifluoride. So 3 fluorine, boron with 3 bond pair because boron only has 3 valence electrons being in group 13 and 0 lone pair remaining. This is going to be 120 degree trigonal planar. So yes, fluorine is very electronegative, but then this dipole will cancel out these other 2 dipoles because you have 3 atoms that are the same in this trigonal planar geometry with 3 bond pair and 0 lone pair. Dipoles do cancel out, it's non-polar. Phosphorus pentafluoride. Penta means 5. There was an earlier question that talked about phosphorus pentachloride. So this is PF5. There are 2 bond angle. One of them is 90 degree between the vertical and the fluorine in the horizontal plane, and here 120 degree because it's trigonoplanar there, whereas it is kind of like linear there. Overall, you get 5 bond pair and 0 lone pair in this trigonal bipyramidal geometry. So again, the dipoles cancel out because if you think about it, this will cancel this one exactly, whereas in this trigonoplanar geometry it's exactly like that, and they will get cancelled out in the plane. So option 3 is also non-polar, no overall dipole. We're looking at A, which consists of 1, 2, and 3 being the correct answer. Question 33, we have carbon in different forms. These are called allotropes. Allotrope is one of those things where it's in and out. The term itself is in and out of the syllabus, so it really depends on which particular syllabus you are doing this in. So just look out for your specification always when you are sitting for exams, and also when you're preparing for exams. Anyway, if I check statement number 2, so we're talking about Buckminster fullerene, which is C60, and then graphene. Graphene is just a single layer of graphite. So what you have is graphite itself is giant molecular. So this one is giant molecular structure. So even when you're single layer, it's still giant molecular. But what is very interesting is this C60 is actually a single molecule. It's a single molecule of carbon, 60 carbon atoms in one single molecule. Okay, so it cannot be giant molecular structure. In fact, it has simple molecular structure. That is why you have a molecular formula, which is the actual number of atoms in one single molecule. So number 2 is wrong because it says C60 has a giant molecular structure. If number 2 is wrong, we're looking at option D, which is only 1 is correct. Question 34, they say carbon monoxide burns readily in oxygen to give you carbon dioxide. If I just write the equation, let's see, CO plus O2 giving me CO2. So all of these are gas, and then I need to balance my equation. So half mole of O2. Of course, you could then write 2 mole of CO, 1 mole of O2, and 2 mole of CO2. It's really up to you. Anyway, if I check option 2, enthalpy change of formation of carbon dioxide. So if I write the expression like this, then I have to show the equation. Form 1 mole of the substance from its elements in their standard state. So carbon is solid in their standard state, CO2 and O2 are gases. Form 1 mole of the substance from its elements in their standard states under standard condition. Now what do I have? I have the formation of CO2, and then I want the formation of CO. Okay, so that is CO gas, carbon monoxide, from 1 mole of the substance from its elements, so carbon solid plus O2 gas, but I need half mole of O2 gas because I'm just forming carbon monoxide. Let's see what is happening here. What can I see? Okay, I think I see what is happening now. Do I? Let's see, if I have delta HF, then I know the formation of the element is 0, and I know this is readily, that is what they say, burn readily. This will relate more to A2 energetics, but you should know that the delta H reaction will be lesser than 0. It's exothermic because you are doing combustion of a substance. So this is the enthalpy of combustion of CO, and enthalpy of combustion is always exo according to, well, whatever you learn in S. All right, so enthalpy of combustion is less than that. What else do we know? We know that we know the enthalpy of formation of CO2. This is the enthalpy of formation of CO2. This is the enthalpy of formation of CO. We know that this is the reaction. So given the enthalpy of formation, then we will have enthalpy of formation of products minus the enthalpy of formation of the reactant. So there's enthalpy of formation of the product minus the enthalpy of formation of the reactant, which is CO, is lesser than 0 according to this particular thing about the combustion of CO. What else can I say? The enthalpy of formation of CO2 is therefore lesser than, if I move the negative term to the other side, I will get the delta HF of CO. So these are all entirely algebraic manipulation, and based on statement 2, the formation of carbon dioxide is more negative. If this is more negative than this, then overall then it's going to be negative, I guess. Does that make sense? It is more negative than that, so option 2 is correct. Anyway, so let's check out option 1. Option 1 is about oxidation state. If we look at CO, the molecule is 0 oxidation state. Carbon plus 1 time minus 2 for the 1 oxygen. Carbon is plus 2. If we look at CO2, however, there's 0 overall oxidation state for the compound and the molecule, which is uncharged. Carbon plus 2 time minus 2, because there's 2 oxygen there. So each carbon is going to be plus 4. So plus 4 oxidation state is more stable than plus 2 because, well, it burns readily. So you want to form this, which is carbon plus 4 from the carbon plus 2. So basically I can talk about readily. Carbon plus 2 go to carbon plus 4. There was CO going to CO2. So option 1 is also correct. Now looking at option 3, what do we know? We are looking at option 3 now. They say 2CO plus, well, they are looking at this equilibrium. They are saying that it's an equilibrium. So we said that earlier it's not equilibrium, but they say that if this is equilibrium, it's going to be very high, the equilibrium constant, because it's going to favor the right hand side, which is correct because they say burn readily. If you burn readily, you're going to favor the right hand side, therefore equilibrium constant is going to be high. So this is option 3 being correct. So 1, 2 and 3 are correct. So therefore we are looking at option A being the correct answer for question 34. Question 35, we have environmental chemistry there. So they say react with oxygen. So if you read the question carefully, they say these are pollutants. They react with oxygen. They react with oxygen on the surface of the catalytic converter. So it is not being asked here, but these are usually rhodium, palladium, platinum, iridium, those really expensive metals. What we have, if we look at option 2, is unburned hydrocarbon. So when you have unburned CXHY, you will plus excess oxygen and you will burn on the surface to give you CO2 plus H2O. So these are cleaner. So CO2 is a greenhouse gas. By no means, it's not an innocent gas, but it does cause global warming and stuff. But these are cleaner than the unburned hydrocarbon. So 2 is entirely correct. If I look at number 1, we are looking at NO2, which is not removed. NO2 is not removed in catalytic converter. So be very careful about this. In fact, we get NO2 from starting the car engine, and we will produce NO2 in the air because starting a car engine during ignition is enough energy to react or to break the nitrogen triple bond in the air, and there will be enough to react with oxygen to give you NO2, which sadly enough is not removed by the catalytic converter. Instead, what the catalytic converter does is it does remove NO, but it does not remove NO2. When you remove NO, you produce N2 and CO2. And of course, that is a classic equation, which you have seen from your IGCSE or O-level chemistry. If 2 is correct and number 1 is wrong because it does not remove NO2 in the catalytic converter, then we're left with 2 and 3. So which means it must be option C. Alright, so of course then if you look at option 3, which you should know how to write the equation, CO burns in excess oxygen on the surface of the catalyst. These are heterogeneous catalysts. What am I talking about? Because these are gaseous reaction and they stick onto the surface of the catalyst where the catalyst is solid. These are transition metals, solid, giant metallic structure. These are all gases. Alright. Next question, question 36 is about redox chemistry. This is the classic disproportionation reaction. So they are under two different conditions. Disproportionation meaning the one species is both oxidized and reduced in the same reaction. Well, actually, yeah, that's fine. This is the mild disproportionation using dilute, cold dilute NaOH, and the other equation given is under the more extreme condition, and you will go to a higher oxidation state of the chlorine. You should be able to balance this equation using changes in oxidation number as required by the syllabus. Well, whatever we do, let's work out the oxidation number in the element, which is 0. The chloride is Cl minus 1 because, it just follows the charge of the ion itself. When you got this one, this is called chlorate 1. It's kind of give it away. It's actually chlorine plus 1. And this is called chlorate 5. So it's chlorine bonded to oxygen. That's why it's got the ATE there. And it's got bracketed the oxidation number. What I'll do now is I'll just very quickly show you how to get that number, being the oxidation state of the chlorine. This is an ion. So the oxidation number of the ion is the overall charge of the ion. So -1 is the overall charge of the ion, and that's the oxidation state of the ion. It's the sum of the individual oxidation state. Chlorine is what you want to find. You have one oxygen. Bonded in a compound is the more electronegative element, being the second period element amongst fluorine, oxygen, nitrogen, the three most electronegative element in the whole periodic table. It's going to retain the -2 charge there. So chlorine is -1 plus 2. Chlorine is +1 oxidation number when you have Cl minus. Cl3 minus, on the other hand, is -1 equal to chlorine plus 3 times -2. Chlorine is -1 plus 6. Chlorine is +5 oxidation state there. We could see that the chlorine 0 has both been oxidized, increase in oxidation number is oxidation, and also reduced from 0 to -1 in the same reaction. So that is going to be a disproportionation reaction where one species is both oxidized and also reduced in the same reaction. So which statements about these reactions are correct? Let's check number 2 first. The products of reaction 1 show chlorine in two different oxidation states. Well, look at reaction 1. So reaction 1, chlorine in two different oxidation state. The products, okay, read carefully, the products in two different oxidation state. Number 2 is correct. So you got chlorine -1 in Cl minus, chlorine +1 in Cl minus. How about number 1? Option number 1, they say reaction 2 requires a higher temperature than reaction 1. In fact, to go to the higher oxidation state, you need a more extreme condition. You need higher temperature, you need concentrated NaOH, whereas this one is cold dilute NaOH. So yes, statement 1 is correct because you need more extreme conditions for the second reaction. Now, statement 3 is about the oxygen in different oxidation state, and that is completely wrong because the oxygen is all -2 and -2, oxygen being more electronegative than chlorine, oxygen being more electronegative than hydrogen. Of course, oxygen can have positive oxidation number when it's bonded to something more electronegative, such as OF2. Then the fluorine will be -1 and the oxygen will be +2 there. But that's not the essence of this question here, so I will just leave that on the side as something which is not directly related to this question. So 1 and 2 are correct, so that means we are looking at option B there. Question 37, so we're looking at which one of the organic compound is oxidized. So this is oxidation by that particular reagent. If we look at option 2, you have that thing called Tollens reagent. So Tollens reagent is a colorless solution. As you know, it's not the copper 2+, it's actually the silver with 2 ammonia around it, and it's a silver 1 complex, so it's colorless. It's got a Cl minus, by the way. It's what happened when silver chloride dissolved in excess aqueous NH3. So that's Tollens reagent. And what you have is an aldehyde, CH3, CH2, CH2, CHO, 1, 2, 3, 4. If you read it, carbon from 4 bond, CH3, CH2, CH2, CHO. Well, important thing is a RCHO, is an aldehyde. When it's an aldehyde, you can be oxidized by tolerance, and you will get silver +1 in the tolerance going to silver 0, which is going to be the precipitate, or you get a silver mirror as your positive test because tolerance reagent oxidize the aldehyde. Similarly, if you look at option 3, yes, I should go for option 1 first, but I can see my aldehyde already. My Fehling's reagent is going to be the blue color solution of aqueous copper 2 plus. It's kind of very similar to the Benedict solution that you use to test for reducing sugar. And as a matter of fact, reducing sugar contain aldehyde. So aldehydes are present in all reducing sugar. So again, when aldehyde is present, the copper 2 plus will go to a brick red PPT, and this brick red PPT is a result of the reduction of that oxidizing agent, because oxidizing agent oxidizes the aldehyde and itself get reduced. You get copper +1, which is copper 1, and you get O2 minus, such that the brick red PPT is called copper 1 oxide. That is how you get the formula back when you were in year 9 doing all-level IGCSE chemistry. Finally, you have option 1 to check. Option 1 is an aldehyde plus HCN under the right condition, which is NaCN catalyst, and under cold conditions like like maybe 0 to 10 degrees Celsius, as the HCN is quite volatile, you're gonna get the cyanohydrine. This is called cyano because of the CN, the hydrine because of the OH. This is a nucleophilic addition. So it is not an oxidation. It is not oxidation, but it's nucleophilic addition. So 1 is wrong. Only 2 and 3 are correct. So there's option C there. Next question, question 38. We have this compound Q, which is added with acidified dichromate 6. So potassium dichromate 6 basically contains the active ingredient, which is this dichromate 6. It basically is the chromium +6, and this is orange in color. This dichromate 6 is a very common oxidizing agent. And then you have, after passing that through it, and then you will pass it through 2,4-DNPH. So I should use a better arrow because that one will imply reactions, whereas this one doesn't. It implies after this stage, then you go to the next stage, which is 2,4-DNPH. Is a test for carbonyl compound, carbonyl C double bond O. This come under aldehyde and ketone chemistry under those carbonyl topic, and you will get a brick red PPT. Oh, sorry, not brick red PPT. What am I talking about? You get an orange PPT, and this orange PPT come as a result of a condensation reaction. So when you condense 2,4-DNPH, you will kick out H2O. Basically, you kick out the nitrogen from the 2,4-DNPH, and you kick out this oxygen, and you would what am I talking about? You kick out the hydrogen on the on the amine there, and you kick out the oxygen. You will kick out water there in this classic type of condensation reaction. So let's go through what is happening there. So if we go through option 2 is CH3, CHOH, CH3. If I translate it into skeletal formula, then I will get this CH3CH, carbon from 4 bond, there's 1 hydrogen there, OH, and then CH3. I have a secondary alcohol because the carbon with the OH is bonded to 2 other carbon. So this is a secondary alcohol. So yes, it can be oxidized by the oxidizing agent, which is the dichromate 6. After that, I have a ketone because the carbonyl, the carbon with the oxygen carbonyl, it's bridged by 2 other carbon. So this one with 2,4-DNPH. In case you don't know what 2,4-DNPH is, perhaps I should draw it out, then you can see what's going on. It's got this thing called a benzene ring, which is not that important, at least not in AS. So it's got a NO2 and another NO2. This is the 1, 2, 3, and 4. So it's 2,4-dinitro. Phenyl is the benzene ring structure, which you will learn more in A2 chemistry. And you call it hydrazine because it's not just an amine, it's also bonded to this thing where it's whole thing there is called hydrazine. So what happened there is, if I pretend all this is just AR, then I'll get AR, NH, then I'll get N, and then I'll get that and that. It is because I have lost the O and the H2 there, and then I'll have kick out H2O. This is orange PPT. So we do get a positive result because you want an orange PPT in the test tube Z, which will only react with ketone or aldehyde. So option 2 is definitely what we want. We can oxidize it, and then it will produce this orange PPT there. Let's check option 1. Option 1 is got CH3, CH2, CH2OH. So CH3, CH2, CH2OH. This is a primary alcohol. The carbon with the OH is bonded to one other carbon. So what happened then is, well, I guess you could produce aldehyde. Or of course, you could also produce carboxylic acid. So you could produce propanel and also propanoic acid. It's a mixture of both. But if you produce this one, in addition to this one would at least, form the exact same thing again. So perhaps I can just use another arrow to indicate that the aldehyde is positive result with the 2,4-DNPH. Positive result, 2,4-DNPH. It's again another condensation reaction to give you this orange PPT. But now, instead of a CH3 and CH3, I should really be careful and say that, I actually get a different product. So it's AR, NHN, and then just like that, I've got a I've got a CH3, CH2C, and then I've got a H there. I still have the H there. Okay, so there's also another orange crystalline PPT, which is a test for aldehyde and ketone there. If you look at option 3, option 3 is very clearly a tertiary alcohol, so you can't even oxidize it. You don't get ketone, you don't get aldehyde after oxidation. In fact, the dichromate, the Cr2O7 2- acidified, it just remains orange. Since you are not producing ketone or aldehyde, you will not get a orange PPT with the 2,4-DNPH. Only 1 and 2 are correct. 3 is wrong, so this leave option B as the only correct answer there. Question 39. So coming to an end now. Chlorofluoroalkanes, blah blah blah. We are talking about radicals. Radicals are species with unpaired electrons. So you're looking for something with unpaired electrons. You're looking for homolytic fission. So you'll be breaking the covalent bond unequally. And these things are very bad for ozone layer. So we don't talk about fluorine radical. This is option 2 because you'll be breaking CF bond, which is very strong. How do I know it's a strong bond? Well, you can have a look at data booklet, or you can think about AS chemistry under bonding. Short covalent bond equal to strong covalent bond. When you think about it, the shorter you are as a covalent bond, the closer your nucleus are to the bonding electrons in between, and therefore the stronger the covalent bond. You can of course check it from data booklet. The energy of a CF bond is greater than the energy of a CCl bond. So it's easier to break the CCl bond and to get chlorine radical, which you can have. And since number 2 is wrong, basically I'm left with option D as my only possible correct answer. Question 40 is about polymerization. Why is this question tricky? So I have 3 isomers. What do I have? I have 3 isomers of C2H2Cl2. Which sequence could be seen within the polymeric chain? So if I start by drawing out this thing, so I have Cl, Cl, H and H. What are the other possibility? I can have Cl, Cl, H and H. So that is the chlorine on the same carbon. When the chlorine are on different carbon, I could also get cis and trans. So obviously, you can appreciate that when the chlorine are on the same side, it's cis. When the chlorine are on opposite side, which is what I'm drawing right now, this is trans isomer. The chlorine on opposite side of the carbon-carbon. This is chlorine and chlorine on the same side of the carbon-carbon double bond. This is cis. And this one has no cis or trans because you have 2 atoms or 2 groups. They are exactly the same on the same carbon of the carbon-carbon double bond. So what sequence can we be looking at? Let me think, is it easier if I start from the option? It might be easier if I start from the option. If I look at option 2, CCHHClCl. So I can imagine this one could have come from, if this is the repeat unit, the chlorine are on opposite carbon. They are on 2 different carbons, so I cannot be looking at these. I can be looking at the cis of the trans, and this will give you that upon addition polymerization. And this is something you will have done from O-level or IGCSE chemistry. How about option 1? So when I look at option 1, let's see, what do I have in option 1? I have CC, Cl, Cl, and HCl. So this looks tricky. Be very careful. They are saying that which one could be the sequence. Could be the sequence. They are not saying the repeat unit. So make sure you do not get confused about this. The repeat unit is not this. They are just saying could be the sequence or will be seen along the polymeric chain. Remember that you have a mixture of all these 3. So it's not either one. It's all of them mixed together. So can you get it or can you not get it? Well, here you have chlorine, 2 times chlorine on the same carbon. Could you get it? Of course you could get it if you get it that one. So your next one will be H and H, like that. Now you have chlorine, only 1 chlorine on the carbon. Of course you can have it, because then you would have, what would you have? You would just have carbon and H and Cl. Remember, this is single bond, so you could have the Cl there or there. It doesn't matter because you can rotate. You can also have the C and what you cannot have is you cannot have these, where the 2 chlorine are like this, and I think you can also have this. Yeah, you can definitely have this as well, because this is another one of these monomer. So 1 is entirely possible. They say could be the sequence or will be seen in the sequence. So 1 and 2 are okay so far. Let's go through number 3. Okay. Probably I don't want the line at all. Let's go to number 3. So what do we have here? We have CC, ClH, and then H and H. We got to try and imagine what could it be. So this one is a CH and H. As you can imagine, then you could have this CH2. That means you have CCO2 on the other one. And of course, it's entirely possible, because remember, this is one possible monomer from this thing. We got 2 chlorine on the same carbon and 2 hydrogen on the same carbon, so it's possible. How about the other one? So 1 chlorine on the carbon, which means you can have another one where the chlorine is on the carbon as well, or you, of course, you can have the chlorine there and the hydrogen there as well. So this is one of these monomer. Doesn't matter which one, because once you form the single bond, you can rotate about single bond, but you couldn't rotate about double bond. Once you form single bond, doesn't matter whether the chlorine is up there or there, they are the exact same thing. So number 3 is possible again. So 1, 2, and 3 are all possible sequences. We are looking at option A as the correct answer there. So that's the end of that 40 question MCQ. As usual, MCQ does take a bit of dexterity in reading questions and breaking down questions. Especially with organic, you got to draw and see it, okay? A lot of students mess up the MCQ because they refuse to write, draw, or circle or underline because they think it's silly, they think it's not time productive. But when you write and circle and do all these kind of little things, they can actually help you in further understanding how MCQ works, because there's only one correct answer. If you're very good at MCQ, it's usually because you know your theory very well, not because you're lucky. Alright, so thank you for watching. Do click the button at the bottom right hand side there to subscribe to the channel, and in this kind of restructured format, that's how the future tutorials will be like. So do share the channel widely with all your friends, chat group, juniors, seniors, relative, and many other people. Follow me at ptet.chemistry. That is at ptet.chemistry on Instagram, Facebook, and Twitter. And get in touch if you are interested in procuring my tutoring services, which would be one-on-one. Okay, thank you for watching, and I'll see you in the next tutorial.